Okay, so now it's the time. I think we can start. So hello everyone. Welcome to take part in European Non-Associative Algebra seminar today. So there are three sessions, and in the first session, there are three talks. So it is my great pleasure to chair the first session. I'm Yunhe Sheng from Jilin University, China, and welcome everyone to come to China for a visit. So you can contact me in the future if you have such plan. Okay, the first speaker in the first session is Professor Bauyrzhan Sartayev from Kazakhstan. The title is Malcev classification of the variety of associative algebras. Let's welcome.
Thank you very much. Thank you very much. And thank you for invitation. And hello for everyone. Good morning for European guys. And good afternoon for Asian guys. Mhm. So today's topic is mass classification for the variety of associative algebras. Mhm. So let me start. Mm. So, as shown in Malcev's work, that work was in 1950. He considered just a free magma algebra, and he considered the space of degree three, and he showed that this space of degree three in magma algebra. So the space of invariant relation of degree three can be decomposed as a sum of these subspaces L1 and the L2 where L1 is a sum of A1 the subspaces of A1, B1, C1, and D1. That actually is direct sum. And these subspaces A1, B1, C1, D1 are defined by the following polynomial relations. So that is the first polynomial relation, as you see. That's A1. That's B1. That's the second polynomial relation. And the C1 that it's two-dimensional invariant subspace, and the D1 it's again two-dimensional invariant subspace. As you see that A1 B1 is just one-dimensional, and so analogically we set L2 that is the direct sum of A2 plus B2 plus C2 plus D2. So how they are defined? That is the definition is the same like A1 B1 C1 D1. The difference that is if in A1 B1 C1 D1 there was left normed bracket, here in the case of 2, here we just replace left to the right bracket. That's just difference. And so you see that as a here dimension 1, 1, 2, 2. So finally the direct sum it gives 6, and here also 6, and finally it gives a whole dimension of magma algebra. Mhm. And why these subspaces are interesting? So the first motivation that's like, as I said before, these subspaces are invariant and under the action of S3 model. And the second interesting thing, why they're interesting, that any identity of degree three, it can be written as a linear combination of these subspaces. Mhm. Now, in this talk, we consider four types, subvarieties of the variety of associative algebras based on Malcev classification. So now I'll explain what we mean when we speak about Malcev classification. We just consider the variety of associative algebras, and to this variety of associative algebras, we just add these identities to these identities by one. And in the variety of associative algebras, these subspaces it can be written in this form. Why we just remove identities and remove brackets, and what we obtain, we just obtain for in the variety of associative algebras, we just obtain four subspaces. The first subspace is A1, and we know that in the variety of associative algebras, A1 it just consists with the A2 because here the difference between them, it just was a brackets, left bracket, right bracket. So in associative algebras, A1 equal to A2. The same thing with the B1, it coincides with the B2. The same with the C1 with the C2 and the D1 with the D2. Mhm. And so, but by these relations, we can define identities in associative algebras. So we obtain only four identities. Someone can ask why it's just four, because you see that this this subspace, or this subspace. Mhm. You see that these two relations, sorry, this identity from this identity, we can obtain these two relations. So the main difference is just here replaced variables b and the c. So from it means that this identity it generates subspace C2, and this identity it generates subspace D2. D2. And using these relations, we define corresponding subvarieties of the variety of associative algebras. And of course, these identities also given in Malcev works in Malcev work in 1950. Now, so definition: an algebra is called first type associative algebras if it satisfies the following identity. Now, let me explain why it's interesting. So we denote by S1 the variety of first type associative algebras. So one motivation for studying algebras, the variety of algebras S1 is the following well-known result. So if we consider the variety operad S1, operad S1, it's just operad derived from a variety of associative algebras with this identity. And we can compute its dual operad. And the dual operad of S1, it will be alternative. It was shown in this work by Jumaldayev Zusmanovich in 2011. And also in this work, there was shown that this operad S1 alternative operad is not Kazoo, and if alternative operad is not Kazoo, so S1 it's like his brother, like it's also not Kazoo. So that's like a motivation for considering S1. Now, an algebra is called second type associative algebra if it's satisfied to this identity, identity generated by polynomial relation of B2. So let us denote by S2 the variety of second type associative algebras. So now, what's the motivation for considering S2? Again, we just consider operad as 2, and we can compute its. If you compute dual operad of S2, then you obtain asymmetric operad. And in work 1, it was proved that asymmetric operad is not Kazoo, and they're shown that the brother of S2 is asymmetric. It was done in 2022 by Jumaldayev and Zahaev. And now let's talk about third type of logical. It's like a third type associative algebras we need to consider. An algebra is called third type associative algebra if it satisfies the following identity. This identity is generated by polynomial a relation of subspace C2. So let us denote by S3 the variety of third type associative algebras. And now let's compute its like a brother. What's the dual operad of S3? So if we compute it, then we obtain left alternative operad with the following identity. So that's identity. Each bracket it stands. This bracket it stands for associator. And so you see that this identity it looks like a Jacobian. So like a Jacobi identity, but relative to associators. So XYZ, YZX, ZXY. And also this left alternative operad algebra with the following identity, it's also some known object. In this work, this algebra firstly was considered by Chelyntsev. So in Chelyntsev in this paper in 1976, and he called such algebras with alternative algebra with such identity. He called -1 algebra. Mhm. Mhm. Now, uh, uh, someone can ask logically now we need to consider fourth type associative algebra, yeah, because we know that we have four subspace A1, B1, C1, D1, but actually there is no need to consider fourth type as associative algebras. Why? Because like a fourth type associative algebra, it's uh, it's isomorphic to the third type. So if we just consider if we just consider the variety of third type and fourth type associative algebras between these categories, we can construct a functor, and it's like a one-to-one functors. If you want, if you we can always from the first obtain fourth type. We just define operation, inverse operation, and under inverse operation you obtain fourth type. So like you see here, that's third type, that's first type, fourth type. If you like consider this monomial, first monomial under inverse operation, it will be CBA. So that is the CBA. Under reverse mapping, BAC, it will be CAB. And this is BCA, it will be ACB, and under reverse mapping, CBA, it will be ABC. So the difference just on sign. And you see that from this identity, under reverse mapping, we can obtain this. So it means that there is no meaning to consider fourth type associative algebra because the result will be the same like in the third. Now, actually, we know that is why associative algebras are so interesting. One reason, because we know that as a under commutator operation, associative algebra it gives precisely Lie algebra. And also, thanks to Poincare-Birkhoff theorem, we know that any Lie algebra can be embedded into corresponding associative algebra. And also, we know if we define anti-commutator in associative algebra, then we obtain Jordan algebra. And we know that the problem of describing all special identities, it's still open problem. So for this reason, it's like the next natural question that's like consider define new operations commutator and the anti-commutator in first, second, third type associative algebras. Let's see what we will obtain. Of course, it's so yeah. Let us consider algebras obtained from first, second, third type associative algebras under commutator, anti-commutator. Let me remind you, commutator operation, that is this, we define new operation, these brackets like AB minus BA. And the anti-commutator, that is this one, AB plus BA. And what we have obtained? Of course, we obtained Lie algebra if we consider commutator, because it's like a subvariety of associative algebra. But here, the main question, can we obtain some additional identities? And now we will try answer to this question. All identities of algebra S1 minus 6. So what's S1 minus 6? It means that as a first type associative algebra under commutator. Up to degree 4, all identities. Up to degree 4 follows from anti-commutativity and the Jacobi identities. So, and an algebra S1 minus, so associative of the first type under commutator, satisfies the following identity of degree 5 and the next identity of degree 6. So you see, in S1, we obtain two, under commutator, we obtain two new identities. And how to prove that these two identities are new? So that doesn't follow from anti-commutativity and Jacobi identity. It's easy task. Just let me remind you the basis of the free Lie algebra. I mean multilinear part. So you see that one of the multilinear bases of free Lie algebra, that's just we fix first you see we fix the smallest generator, that's A, and all other generators we can just write all possible zero permutations. And you see that as a linear combination of all basis elements. So you see, and it means that as a each monomial, it's base monomial of freely algebra. So it's like a new identity of degree 5. And it's not so difficult to see that Lie algebra with this identity of degree 5, it's not nilpotent, but you see that in degree 6 we obtain this new identity. It's like a nilpotency of index 6. And so that's like a new identity which doesn't follow from anti-commutative Jacobi and this identity of degree 5. And if in degree 6 it's like a nilpotent, so it means that there is no reason to consider to search all other identities in 7s, 8s, and so on, because that's all 0. So now let's talk about anti-commutator. Let's talk about anti-commutator. If we consider associative algebra as the first type under anti-commutator operation, up to degree 4, all identities, it follows from commutativity and the following identity. So that's like a Jacobi identity, but relative to the anti-commutator. And sometimes such algebra, I mean algebra with the commutativity and with this identity, sometimes it's called Monk-Lie, sometimes it's called Jacobi-Jordan. So that's like something we'll know, something known class of algebras. And at degree 4, we obtain this identity. And there is no identity of degree 5. I mean, there is no new identities. And in degree 6, we also obtain nilpotency of degree 6 under anti-commutator. I'll later explain why we always obtain this one. I mean, in the case of first type associative algebras. Now, and the next problem that's like consider the same problem we consider for the second type of associative algebras. All identities of associative algebra of the second type under anti-commutator, all identities up to degree 4. It follows from anti-commutativity, Jacobi, and the metabelian identity. When we speak about metabelian identity, that is the identity of this form. That's like this identity also is known like solvability of step 2, as I remember. The solvability of step 2. And now, what about anti-commutator? Of course, guys, we hear this theorem just tell us that all identities only up to degree 4. If we speak about other identities like degree 5, degree 6, degree 7, we also, that's new result, we recently, it's proved that there is no other identities. It's not still somewhere placed, but we have proved that associative algebra of second type under anti-commutator, it's just metabelian. There is no other new identities. No new identities. Okay, maybe we'll publish it in near 2-3 months. Okay. Now, but of course, let's make one remark. This algebra is not nilpotent. So you see, it's like someone can think that as in the first type of associative algebra, it was in nilpotence of degree 6, but this metabelian Lie algebra is not nilpotent. Now, the next one. What about second type associative algebra under anti-commutator? Up to degree 4, it follows from commutativity and the following two identities. So the following identities. Now, someone can ask the question, what about degree 5, degree 6, degree 7? That's also a new result, not published, not placed anywhere. That is, we also have new identity of degree 5 in the case of second type associative algebra under anti-commutator. We also obtained new identity of degree 6. And it's also, it seems that it's, and it's like an open problem that we don't know about degree 7 but we have a hypothesis that there is also new identity of degree 7. So you see that here the situation is completely different. Like here at degree 4, it's like ends the list of identities. But here, a new identity of degree 5, 6, and so on. It's not given here. Mhm. Now, and so the second type of social algebra, it's the most interesting, relative to commutator and the anti-commutator uh, algebras. Now, what about third type? What about third type? All identities of third type associative algebra under anti-commutator, uh, it follows from anti-commutativity, Jacobi, and this nilpotency. Here we again obtain uh, nilpotency of degree 4. Now, what about anti-commutator? All identities of algebra, a third type of social algebra under anti-commutator up to degree 4, it's from commutativity and these four identities. Four identities and of degree 4. Here, this algebra under anti-commutator, it's not nilpotent. It's not nilpotent. I will show it later why it's not nilpotent. So, that's like a remark that I said before. There is no need to consider the variety of associative algebra satisfying 8. 8, it means that is the algebra of the fourth type. Because since the algebra of the third type, free algebra, isomorphic to the first type, and the remark define opposite operation. Mhm. Now, let us summarize so all given results. It just like a just make conclusion like a what so why Malcev classification? Why Malcev classification? It's so interesting. Let me explain it. Because you see that as a if you consider so we consider Malcev classification for the variety of associative algebras. So that's the first type, second type, third type, fourth type. So their dual operads, it's always obtain something well known and something some interesting algebras. Like in the first case, alternative, here as a symmetric, here's minus 1 algebra, and here also that's minus 1 algebra. And here is given that all results are not causal, so this opera is not causal. And under commutator, here we obtain Lie algebra with identity, additional identity of degree 5, 6. Here's metabelian algebra, here nilpotent algebra of index 4, nilpotent algebra of index 4. Actually, this algebra also Lie with a nilpotent index 6. So only in the second case, we obtain non-nilpotent Lie algebra. And under anti-commutator, that's Mokli algebra, but it's also nilpotent. Here we obtain under anti-commutator Jordan algebra with some additional identities of degree 5, 6. It's not nilpotent. And these two algebras are also some additional identities, and these algebras are also not nilpotent. Are also not nilpotent. Now, in one, it means this work, Marco and Rem, in 2006. It was shown that by decomposing the associative product, decomposition of associative product in this way, so the associative identity becomes equivalent to the following two axioms. So this decomposition, such decomposition, is called parallelization. So what is the main idea of polarization? Polarization, it means that is the method of writing non-symmetric. So you see that associative product, it's non-symmetric. And the method of writing non-symmetric binary operation as a linear combination of symmetric and anti-symmetric operations. And so this associative relation identity, it's equivalent to these two axioms. And now the next question, that's like, what will be polarization of first type associative algebra, second and third type? So the polarization of S1, S2, and S3 are given by the following additional identities. Of course, as S1, S2, S3, it's firstly associative algebras. For this reason, in their polarization, there are also participate these two identities. And the question is, if we calculate the polarization of S1, S1, S2, S3, what we obtain additional axioms. In the case of S1, additional axiom, it will be this one. So just like axiom of Mauchly algebra. In the case of S2, the polarization, for the polarization, we obtain this new addition, so this additional identity axiom. In the case of S3, we obtain these two. So that's like a polarization of S1, S2, and S3. Now, as I said before, here it just relative to commutator. The most interesting algebra, that is the second type, as I said before, because here it's like a nilpotent of index 6, index 4 nilpotent, index 4 nilpotent. So the most interesting is the second type of associative algebra. Now, what we will do, we will try to construct its basis of the free. Now we consider the free associative algebra of the second type. So by S2, we denote the variety of second type associative algebras, and the corresponding free algebra of this variety we denote by S2x. So that's just free algebra from this variety generated by the set X. Now, in algebra S2x, the following identities hold. So we have this identity of degree 4, and here this identity of degree 5. We just removed here brackets because it's associative, so there is no any brackets. We don't need any brackets. And now you see that this identity of degree 5 it's so interesting. Now let me explain why it's sorry. And from this identity 10 and the identity 11, from these two identities, we can obtain this identity of this form. We can obtain this identity of this form. Now, the identity at 11 implies that associative monomials in these associative, in arbitrary associative monomials with where n bigger or equal than 5, the generator xi2, xi3, and xin minus 1 can be ordered. So the leftmost generator and the rightmost generators, we fix them. But this generator which stays between them, we can order them in like a increasing order. Why? Because you see here in identity 11, here A, E, so leftmost and the rightmost generators fixed, and here BCD, BDC, and the CBD. So we can place them in any order. So we can order them. So the spanning set of algebra S2x is the associative monomials with ordered generators given above. We mean this one. So every monomial from the spanning set is represented. We can represent it as follows. So if you have such monomial, you can just represent it in this form. And so just its leftmost generator, and that is the rightmost generator. And this identity 12, by this representation, we can just write it in this form. AE is equal to AD minus BD minus BE. So this identity 12. Now, let me just explain one combinatorial thing. Let represent this identity of the form 13 by graph. Since in 12, I mean this 12, C, the generator C, you see generator C, occurs in neither the first nor the last position. The row 13, we mean this, row 13, implies two associative monomials for arbitrary lengths. So we can just, this row 13, it works for for arbitrary monomials, for arbitrary associative monomials with arbitrary lengths. So not arbitrary monomials, just for arbitrary lengths. Why? Because you see C here, it stays not first and not last. So instead of C, we can just place any monomial of any length, and we can obtain such rule for needed lengths. Mhm. So indeed, the rule 13 can be illustrated as follows by graph. So firstly, like we consider these generators as vertices. We consider this. So we have here A, E, D, and B. We have four vertices, A, B, D, E. And here, if you want to achieve from E to E, if you want to go from E to E, so from E to E, how we can achieve from E to E? We use these three paths. Firstly, we go from A to D. So you see, from A to D. And then the next step here, the sign. So it's like logically, if you want to reach from A to E, here the arrows, it must be from B to D and from B to E. Of course, logically, it must be like that. But here, since we work in some strange, not strange, like a unusual object, for the reason, if you have here a minus, for the reason here we have from B to D. So we move in opposite side. And here from B to E, it's like this one. So this like identity, it can be represented like this graph. From E to E, it's like from A to D, from B to D, and from AD minus BD plus BE. So yeah, to reach the vertex from E to A, from E, not, it's mistake. From A to E, the rule proceeds through the two intermediate arbitrary vertices. So if you want to reach from A to E, we just fix two arbitrary vertices here, BD, here BD, and the signs BD has a sign minus the arrow illustrated from B to D. Like explanation of identity 13. Now, let us define the set. Let us define the sets A1, A2, A1, A2, A3, A4. We define the set as follows. So A1 that's just generators, A2 that is just these pairs. Now, and there is no any conditions for these indices. Now, we define the set A3 in this form, and to the indices, we here define the following condition. And the A4 we define as follows. That is this set with the four indices, we define the following condition. And the starting from degree 5, where n bigger or equals to 5, we define an in this form. An is defined as follows. So that is this one. X I1 XR, that is, so that is, we know that is every associative monomial in second associative type associative algebra of the second type, it can be represented in this form. So we define in this way, XR, XI1, XI2, XI3. And here, the condition defined on these indices, that is this one. R, it can be any, index from 1 to n, I1, and I1, it's smallest index. So here it means that we place smallest indices, and here we just the pair with the smallest index, it can be we place instead of XR any generators. So you see this condition. I1 is smallest index, and the pair to the smallest index, it can be any generator. And also we add here additional, we have here additional monomial xi2, xi3. We just add additional monomial xi2, xi3. Now that is a set definition of an. Also, we said this one, the big A. Big A, that is the union of all these sets. Now, and example. In the multilinear case, let me show you how to define A5. So as I said before, that is here we have xi1 and the r xr I1. So it means that here will be it will be x1, x2, x1 in multilinear case, x1, x3, x1, x4, x1, x5, x2, 1, x3, x1, x4, x1, x5, x1. So you see that we have all possible pairs with the x1 and the other vertices, sorry, generators, and here when x1 is left side stays and the right side stays. And also we add this additional monomial. So here it will be x2, x3. The same idea for a6. Here it will be these monomials 1, 2, 1, 3, y4, 1, 5, 1, 6, 2, 1, 2, 3, 2, 4, 2, 5, 2, 6. Sorry, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. And also we always add this additional monomial. Then the set A is the basis of algebra, the basis of the free algebra, of the free associative algebra of the second type. So that is the basis. And from this theorem, we obtain such result that the dimension of associative operad of the second type in degree 1 it's 1, in degree 2 it's 2, in degree 3 it's 5, in degree 4 it's 9, and starting from degree 5 we have like a universal construction. And oh sorry, I can move it. I can move it. So and starting from degree 5 we have the following dimension, I mean of operad, or you can understand it as a multilinear part. Why this is the case? Because you see that as a starting from degree 5, in each degree we just add. So you see in degree 5 here it was 9 monomials, 9 elements, and in each degree we just add new pair. So here it was, so you see here, if we add new generator, here it means that it will be x1, x6, x6, x1. We just add 2 new elements. Here it's 1, x6, 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 x1. And in the next in the next consequent degrees, we just add by 2 new elements to obtain the basis of this algebra. Now, let me explain combinatorial meaning of this algebra. Combinatorial meaning. Combinatorial explanation of the theorem. Of course, this combinatorial explanation, it works only from degree 5. Why it works only from degree 5? Because we have such beautiful identities, such beautiful explanations only from degree 5. And beginning with the degree 5, regarding the generator set X, as a, so we just consider the generators as a vertex set of directed graph, and we interpret each monomial xi xj as a directed edge. So it's like an edge directed from vertex xi to the vertex xj. In degree 6, in degree 5, we obtain d graph. So the d graph, that means this x, that is a set of vertices, this A5, that is a set of edges. And why is this? So you see that is like this, actually these basis monomials in our graph, it defines our paths. I'm not sorry, directed edges. And this graph is strongly connected by theorem 13. So that is it. Sorry, that it's not given here number. So that's like by this theorem in degree 5, this graph is strongly connected. Why it's strongly connected? It just like follows direct from definition, because in the basis, what's the meaning basis? Basis, it means that as any monomial can be written in unique way as a linear sum of this any monomial. Any element here can be written as a unique way as a linear sum of this set. So you see that as it means that as so from any, so it means that from any xi, there is a path to any xj. And from degree 6, what means if we consider degree 6? It means that as we add new vertex x6. Initially, this new vertex is isolated, and to preserve strong connectivity, it's necessary, it's insufficient to add 2 new edges, x1, x6, and x6, x1. And indeed, x1 is already reached, and it's reachable from every other vertex via edges in x5, a5. So O, I, and J have a path. So if you want to reach from any other vertex x6, you first, if we add these two paths, you first say from xi go to x1, and from x1 we can go to x6 by this. And conversely, if you want to go from x6 to any other vertex, we use this one, and from this we go to this by a5. And inductively, we can continue to any number of vertices. So if we add x7, x8, x9, the same inductive steps implies when they join each subsequent new vertex. So that's like a beautiful combinatorial explanation of the free second type associative algebra. Mhm. Now, uh, now what we did, we constructed the basis of the free second type associative algebra. Now the next logically what we need to do the next step. We need to consider free algebras of the first type associative algebras and the third type associative algebras. Yeah. Second, it's like the task is finished now for the first and the third. Before we said that, I just remind you, before we said that second, uh, uh, I see. Oh, sorry, it's mistake. Here must be three. Oh, I see that's something wrong. So here must be three. Now let's talk about third type. Before we said that the algebra S3 under anti-commutator satisfy to the following identities. Third type. And also, let's consider uh, let's consider some identities of the mixed identities relative to commutator and the anti-commutator. If you consider third type associative algebras, with a we can consider mixed identities. So here you see here participate in this monomial participates commutator anti-commutator. Here also two anti-commutators, one commutator. Here two anti-commutators, one commutators, which commutators stay inside, and here two commutators, one anti-commutator. No matter, all these monomials in third type associative algebras are zero. And also this one. Of course, that is the monomials of the form when it looks like a metabelian. Yeah, you see here. It's not. It's like two generators multiplied to two. And if you consider left normal, all these monomials are also equal to zero. And here we just consider only monomials relative to anti-commutator and the commutator when the monomials have both multiplications. Both multiplications. When in the monomials participate both multiplications. But here, if here participate only anti-commutator, they are not equal to zero. So let oh, where is L? Where is L? Let us define the set B1, B2, B3. So the set B1 it just initial alphabet. B2 that is this monomial and this monomial. B3 that is these four monomials. And starting from 4, we define Bn in this form. It's just monomial of the following form. And here we define what we define. We define condition on indices, that is these conditions. And here the condition to these indices, that is this one. So this condition on index, it means that it's strongly increasing. I mean, the generators here are strongly increasing. Also, we define the set big B that is just union of all of these sets. Now, this set B is the base of algebra as 3x. So the set B is the base of the free associative algebra of the third type. So, and from this theorem, from this theorem, let's just write the dimension of this algebra. I mean, multilinear part, of course. In the degree 1, it's just 1. In degree 2, it's 2. In degree 3, it's 4. And starting from degree 4, the dimension is just 1. And this result shows that starting from degree 4, the free third type associative algebra third type behaves like a free associative commutative algebra. Because you know that the associative commutative algebra in any degree it's like a dimension, it have dimension 1. And here also starting from degree 4, the dimension is 1. Now, so we just described the free associative algebra of the third type. Uh, uh, so it's just a little corollaries. A free nilpotent algebra of degree 4 can be embedded into free algebra from the variety of R3 under the commutator. The free Jordan algebra with the given identities can be embedded into algebra from the variety of R3 under the anti-commutator. So it means that if we consider a free third type associative algebra under anti-commutator, then we have only these identities and there is no other identity. And now let's talk about first type associative algebra. In first work by Lopatin in 2005, he constructed the base of the associative algebra of the first type. So this task was done before by Lopatin. So that let me remind you that the associative algebra, that's the algebra with this identity, and he proved that associative algebra, free associative algebra of the first type is nilpotent of degree 6. And this result made by Lopatin, it explains why this associative algebra and under commutator and under anti-commutator it's nilpotent, because initial algebra was nilpotent. For this reason, there is no any surprises why commutator and the anti-commutator algebras are also nilpotent in index 6. So now the next one. So that is like a 4 type of associative algebras. Actually, in every my talk, I try to finish with some interesting picture. So here I do. If you want to learn 4 type of associative algebras, just learn these 4 rabbits. This type of why I just choose these 4 rabbits, like they're similar. You see, their difference is just maybe color, because relative to first, because we know that third and the fourth associative type algebras, third and fourth, they're isomorphic to each other relative to reverse operation, and also we know that relative to commutator, they're also looks like a similar. They're not absolutely like the same. They looks like a similar. Why they looks like a similar? Because the first type is a nilpotent relative to index 6. Fourth and five also nilpotent of index 4. But second, it's like a special. It's not nilpotent. And now the next natural questions. Of course, today I try to give motivation why Malcev classification it's so interesting for the varieties of algebras. Like today I just explained here by this, I try to give motivation here why Malcev classification is so interesting, because you see that here relative to dual operads, it gives some natural objects that all algebras know, alternative operator, associative, and so on. Sorry, associative and so on. For this reason, it's like a natural to consider Malcev classification for other varieties. Of course, the next natural question, it can be like a classification, multi-classification for the variety of some readmissible, because we know that the variety of associative algebras are readmissible. So we can consider another varieties of readmissible algebras, like, for example, Preli, or someone knows like right symmetrics or left symmetric, no matter. And I have 5 minutes, so let me just show you I, I have 5 minutes. Yeah, is it correct? Or 10?
I think five. Okay. Yeah.
Okay, fine. So, and the next step, that's why consider multiple classification for other varieties. So here we just considered, we here considered multiple classification for the variety of left symmetric algebras. So it's again the same idea. If you want to consider multiplication for other varieties, the idea is the same. Just first you take the variety of right Prelie algebras, so it's like a left symmetric, and on this Prelie algebra you define like a, you add new identity to this Prelie algebra, and you obtain subvarieties. So for subvarieties of Prelie algebras. So, and also, if here in this work, like uh, we consider Prelie algebra with identity A1, Prelie algebra with identity B1, and the Prelie algebra with identity A2 and B2. And considering such objects, we again obtain something interesting. For example, if you consider A1 left symmetric algebras, for example, if we just consider so what will be his brother? When we speak about brother, I mean about its Kazoo-Duo operad. Then that is a, oh, sorry, maybe that is a left symmetric algebra with a identity A1. Then its Kazoo-Duo operad, it will be a left alternative operad with identity left commutativity. If you just compute, you see that's like something again, some well-known objects. I mean, when I say well-known object, it means that the alternative operand, of course, it's known, and the left commutative identity, it's also known. So that's like a combination of two varieties, like a intersection. And let's talk about, and here also some beautiful identities, no matter, I don't have enough time for this. Let's consider left symmetric Prelie algebra with the identity B2. Again, it's dual operand. It will be asymmetric operand with again left commutative identity. So it's Kazoo dual operand of left symmetric with the B, it's asymmetric with the left commutative identity. And if we consider left symmetric operand algebra with of the type A2, then its brother Kazoo-Duo operand, it will be alternative operand with this identity. I call this identity as commutator is a left center. Why is the commutator left center? Because we can write it as if you send this monomial to the left side, we obtain AB minus BA. Just commutator multiplied to generator C, it's 0. So like a commutator is the left center. It's like introduced in a lot of works, like in Jumal and so on. So it's like again alternative operand with the following identity. So for this reason, yeah, that's like you. I just want to say that multiple classification. It's something like a something like interesting. So thank you very much for your attention.
Thank you very much for the nice talk. Uh, are there any questions or comments?
Let me place this picture.
If no questions, so let's thank the speaker again. Thank you very much. And now let's have probably 5 or 6 minutes break. So yeah.
Mhm.
Okay, so see you soon.